So welcome everyone to the TILOS seminar. It's a great pleasure to introduce Sharif Rida, who's a full professor at the School of Engineering and Computer Science Department at Brown University. He's also a principal research scientist at Amazon. He joined Brown in 2006 after receiving his PhD in computer science from UC San Diego. And he has over 135 research articles in the areas of energy efficient computing, electronic design automation, and combinatorial optimization, as well as several patents. He's received, as you'd expect, many research acknowledgments and awards, including 8 Best Paper nominations, 3 Best Paper awards, the NSF Career Award. He's been PI or co-PI on over $20 million of funded projects from federal agencies and industry corporations. He's a senior member of IEEE. Right. It's a pleasure to have Sharif here and take it away.
All right, thank you, Andrew, so much. So there's one thing I would like to add to this. For this is that Andrew was, of course, my PhD advisor when I was back in UC San Diego, and that's how I learned all that combinatorial optimization tricks from him, basically. So I owe him whatever I learned in that space from him, really. All right, so we'll get to this talk today, how to use machine learning for combinatorial optimization. It's obviously a hot topic these days, and for good reasons. Before I actually start, I would like to first acknowledge Abdurrahman Hosni, who's a PhD student in my group. We work together on this topic, and he's basically been the lead on the case studies that I will describe, and Abdurrahman is here today also in this talking case. There could be interesting discussions and questions afterwards. So basically, what are we trying to do in here? We're all familiar with the combinatorial optimization space. We got integer linear programs, network flows, Markov processes, meta-heuristic, etc. And that's been going on right now for maybe 70 years. And then we have the machine learning space, which has been going also for a long time, but it has gained a big momentum in the last few years with deep neural network and other techniques. And there's a whole bunch of techniques in that space. And we're looking at that intersection between those two. How can machine learning help combinatorial optimization? Now, why would we do that? Well, I mean, right now, basically, the current problem is that combinatorial optimization obviously has scalability problems. A lot of these problems are NP hard and they take forever to run. And in many actually industrial settings, we're basically solving the same problem every day with just small changes. And we're not leveraging the solutions from the previous day towards improving the quality of the results or the runtime for future days. Hypothetically speaking, let's imagine you're working in FedEx or United States Postal Service, and you have every day to plan the routes for your delivery trucks. You're doing vehicle routing problems every day. What's changing between one instance today and tomorrow? Maybe transportation costs. Fuel changes a little bit. So as a result, the different coefficients in your integer linear program just changed a little bit since yesterday. And can't we just use the solution from yesterday to speed things somehow when we solve today instead of just solving it from scratch or to improve the quality of results? So that's kind of like the main exploitation that we want to use in here. So we basically want to leverage machine learning models for combinatorial optimization. And there's 2 things in here we can do. If you're solving the problem to optimality, then we want to improve the scalability. We want to solve bigger problems to optimality. We want to reduce the runtime to get to the optimal solution. Or if you have a time cap and you're just getting the best solution you can get from your algorithm within this time cap, then we also want to improve the cost or the quality of results within this time cap. So that's basically what we want to do for this machine learning for CO, which is ML for CO. Okay. So I tried to kind of group the main research directions in that field in basically 3 buckets, okay? And, I'm trying to summarize the research directions that are happening in each one of those buckets, and I will give 2 case studies based on the research that I've been doing with Abdurrahman. So the main 3 categories is that, first, one option is to use the machine learning to set up the problem for the combinatorial optimization. So you can think in here, you have a problem instance, then we give it to the machine learning problem before we run the combinatorial optimization. And then the machine learning problem can give us a lot of information that I can describe that can help us with the optimization solver. The second big bucket is to use the machine learning to assist combinatorial optimization. So we have the problem definition in here. We have an operation research combinatorial optimization problem. And in here, the machine learning algorithm is being used in the loop. So as we're making sequential decisions in the optimization algorithm, we're invoking the machine learning in the loop in here. The last one is that we're actually going to use the machine learning algorithm instead of in essence, we're replacing the hard rules that are in the typical combinatorial algorithm with a learning environment that learns what is the best action or decision to make in a sequential process. So that's the three main buckets that I will describe. So let's start with the first one. So in the first one, we want to use machine learning as a separate step before the optimization algorithm. So we give the problem instance to the machine learning model. What can we do that in that case? Well, in some cases, actually, in most production flows, this is actually the typical thing being done in production flows. All the coefficients in academia, we usually get an ILP. The coefficients are already given to us. The objective function coefficients, the constraint, all of these numerical values are actually given to us. But in reality, in production flows, all these values are coming from machine learning pipelines. So there's a data pipeline that processes previous data and actually generate these coefficients. And a good example, for instance, like say this vehicle routing. If you're doing vehicle routing and you care about transportation costs, say tomorrow, what will be my routes tomorrow? What will be my routes on the weekend? Well, let's guess what? These costs will be function of your fuel cost. How can I get fuel costs? Well, I need to actually have a forecast algorithm that tells me what are my fuel costs, and that's what's going to determine the coefficients in my problem. Also, my cost will be a function of how much labor do I have, how many people will show up on that day. Well, in that case, I need a labor pipeline to predict how many people will show up on that day given historical data. So in reality is, you will see in most industrial flows that the input itself, the problem formulation itself with the coefficients, and it is coming from a machine learning pipeline. And that actually is forecasting because you're solving a problem for the future, like a planning problem, a network problem, and so forth. So that's one approach to use machine learning to set up optimization. The second one, which I will describe in our test case, is to determine the hyperparameter for the combinatorial optimization algorithm. So for instance, ILP solvers have hundreds of configuration parameters that determine how fast they run or the quality of result given a certain time limit. So in that case, or maybe for instance, you have simulated annealing and there's hyperparameters such as the cooling schedule, etc. So in that case, maybe the machine learning model can run before the optimization algorithm to tell us what would be the best configuration for this particular problem instance. So we're not using the default configuration or the default hyperparameters. We're getting this problem instance and we're saying, we've seen this problem before. And when we saw it in the past or something similar to it that we've seen in the past, and when we saw something similar in the past, we use these hyperparameters. So therefore, let's use it for this problem as well. And that allows us to configure the optimization solver. A third direction is to actually make some prior decisions for us. So for instance, you're solving a combinatorial problem, say traveling salesman or an integer linear program. Maybe we can, before we run the optimization solver, we can basically set some values for the variables, make some decisions a priori for the variables, set some to 0, set some to 10, whatever it is, those values. And that would be based on something we've learned in the past. We've seen this in the past, and 99% of the case, it was this value, or we can build a model for the values of a certain decision parameter, and we can make say withdraw a value from that distribution, or have a decision tree that based on these certain states of the instance we're getting, we should decide on that value. So in that way, once you kind of basically make this prior decision, you reduce the size of your problem, or even better, you can decompose the problem into some problems and solve parallel and independence. Another technique that people use also in that area, and I've seen it in so many fields, robotics, there's so many people using logic synthesis, a lot of people are using this idea, is that in some case you might have at your repertoire a number of heuristic optimization algorithms that you can use on the problem. And in some cases, of course, these heuristics, some of them dominate some others, but some others are not dominating. Like it depends on the problem instance, the best heuristic could change. So how can I select the best heuristic for my problem? Well, in that case, we can use machine learning as an oracle that allows us to kind of basically, here's a bunch of algorithms, instead of me running them in parallel and figuring out which one is the best, I can then just pick one of them a priori. And in that case, the machine learning tells me, okay, this is kind of the right heuristic to use for this particular instance. In all these four cases, except the first one, which is just using the coefficients and generating the coefficients. We need to encode the problem structure in a way that facilitates this machine learning, right? If you're doing machine learning models, say based on a graph, then in that case, you need to encode the problem in a graph. And also we need a priori training data, and that was the main motivation to run this. If you run a company and you're basically running the same problem instance from the same problem distribution every day, then you really had a lot of a priori data, training data that you can use. We can also use unsupervised learning. Maybe you can cluster variables in your decision problems and substitute these cluster variables by just one. And basically run your optimization problem in a smaller instance, and when you get the results, you go back and assign all these variables in the same cluster with the same value, and so forth. So this is all kind of like the things that we would need to do in order to go with any of these directions in here. So I want to present actually a case study that I worked on with Abdurrahman, and in here we want to configure an ILP solver. So we have an ILP solver in here. And like I said, the performance of the ILP solver, you can think of it this way. If you leave it, of course, sometimes the instance is so big, you can leave it to run forever. So in some cases, we either want to improve the runtime until we reach optimality, or given a certain time cap, we want to find the best solution within this time cap. And we're going to be working with the second case because the instance we're dealing with is so big. If you actually look at any ILP solver, you will find tens or maybe even hundreds of parameters that are basically hyperparameters for the ILP solver, and that you can tweak to control how that solver behaves. I was actually looking at the SciPy ILP solver, which we're using, and it's like has tens of pages. Each page has like tens of different configuration parameters, and we use the ones that I basically described that I'm putting on the screen in here. So, you know, what are the values in here? If you have a time cap of 15 minutes on your instance, how can I get what configuration should I use to actually get the best solution? And actually, there's algorithms for that. There's a popular tool we use, which is called SMAC. SMAC figures out the best values for these parameters, but it takes a long time to actually figure out what is the right values for these parameters given a certain set of problem instances. So it does searching in there. So, and actually you can see in here, for instance, if you try different configurations on, I will take one problem instance in our benchmarks, which I will describe, and you try to apply different configurations, and sure enough, you're going to see the cost of the problem that you get within this 15 minutes, highly dependent on which configuration. And if you just apply the default configuration for different problem instance, and you're trying to search for the best configuration, say with the SMAC tool, then you will get highly different results. So you can see that there's a big improvement in the cost that you get as a function of this configuration. So we really didn't need to search for the configuration. But the problem in here is that if we all search for the configurations over and over and over, then we're not using much of the machine learning. What we want to do is that I've been solving the instances from the same problem distribution for the last 100 days in my company, in my production line. And for every day, I have been getting the best configurations for each one of these problems. Now I'm getting a new problem instance. I'm getting the vehicle routing problem for today with the new fuel cost projected for next week. And do I need to run this whole configuration search algorithm again? Can I use all the information that I accumulated over the last year to actually help me pick a good configuration without me basically doing the search again? And that's the goal of the paper in here. It's under review, so I hope, I know this is a smaller meeting, so I hope appreciate the confidentiality. I don't think it's a problem sharing these early results with you. So we basically want to shortcut the search process. We basically want to leverage configurations that we found in the past for similar instances on this new instance we've got. So the basic outline is pretty simple. We're going to take this new instance, say I, look at our problem instance before that we have in our training data set or like from previous days, and pick a similar one. And that's where all the secret sauce is. How do we pick a similar problem instance to the one that we've just got? And then maybe we can select the k nearest neighbor in that similarity space, maybe 1, 2, 3, and then we get this configuration, say, from the nearest neighbor and apply it to this new instance and get the cost. And that would be the end of the story. So we don't need to do hyperparameter tuning or searching. We're just taking this configuration and applying it. So as I said, the secret sauce really is how can we measure the similarity between two mixed integer linear problem instances for the purpose of choosing an a priori computed configuration. So here's like one of the basic assumptions we make, and we validate later, and we'll show it makes sense. Suppose I have two problem instances in here coming from the same distribution. Again, like, I'm using vehicle routing as an example. You could have also routing in circuits and so forth. The two instances are coming from the same problem distribution. It's the same network, just different coefficients, or maybe one variable is different than the set, or two variables. So it's coming from the same distribution. The hypothesis in here is that if I have two different instances and I solve them with the IMLP solver and with the same configuration, and I get costs that are similar, meaning the two numbers are actually similar, I get 100 from here and 100 here under the same configuration, or 100 here and 110, then in that case, if I have the best configuration for instance 1 and I apply it for the instance 2, in that case, I automatically get the reduction in the cost on the right-hand side, because basically the two costs are correlated with each other as a function of the configuration. I change the configuration and the two costs are correlated. This one goes up, this one goes up. I apply another configuration and the two costs goes down. This cost goes down and this cost goes down. So as a result, if I can find the best configuration for instance 1 from prior days, I know I can apply it on instance 2 if I receive instance 2, say, right now. If I'm getting instance 2 right now, I can apply the best configuration from the past because I know the two costs are basically the same. But of course, we don't know the cost in advance. We can know it from our training data. So from our training data, I can look at past instance and I can figure out which instance have the costs going up and down together as a function of the configuration. But when I get a new instance, I only have my training set, and my training set have instance and cost. My new instance is actually something that I want to figure out the cost for. I have no cost for it. So what we really need to do is to learn a metric that I will describe that allows us to basically identify which instances are similar to each other. That is, they are likely to produce cost that goes up and down in the same direction as we change the configuration. So that's basically the goal, because during runtime, I'm getting instances, I'm not getting cost. So this is the flow in here we're proposing. We're going to have instances that we've been running, say, that, every day you've been solving this problem, this vehicle routing problem, hypothetically. And you're going to be basically looking at all the instances we've solved before under the same configuration. Then we're going to identify in these instances, for each instance, we call it anchor. We're going to identify two other instances. One is positive and one is negative. A positive instance is basically an instance from my training data set that had a cost very similar to that anchor instance. And a negative instance is an instance that has a cost that was very unsimilar to the one that's my anchor. So we want to find two other instances, one close enough in the cost, and the other one has a big difference in the cost. Okay. Then we're going to take each one of our ILPs and encode it into a graph. So like I said, if you're going to do apply machine learning, we need to basically take our problem and convert it into a model that can facilitate machine learning. So we're going to take ILP instances and convert them into graphs, a bipartite graph to be exact. Once we have the bipartite graph, we need to extract features that's going to be used to encode that graph and use it for the machine learning algorithm. So we're going to run a graph convolution algorithm, which I will describe, and that's going to convert each graph corresponding to an instance into a vector. And that vector uniquely kind of think of it as summarizing the properties of that graph. If you stop at this point, there is nothing that would say that vectors from two similar instances, that is two similar instances that produce the same cost or similar cost under the same configuration, that those two vectors actually will be similar to each other. There is nothing that says that. So the last step we do is we call metric learning. And in that metric learning is really where the most of the juice of the algorithm is. Because we want to project those vectors we're getting for the different instances into a space such that instances that have similar costs become close to each other in that space, and instances that have unsimilar costs will be far from each other in that space. So for instance, in this graph, the anchor instance, the first instance is the black one. The positive one that has cost similar to it is the green one. And the red one is the instance that has cost that is far from it. And of course, because those were calculated with the graph convolution network, there is nothing that says that those two things, the green has to be close to the black and the red has to be far from the black. But once we do this metric learning, we do this projection of vectors into the new space, you will see that now instances that have similar costs became close to each other. The green is close to the black, and problem instances that have unsimilar costs are actually far from each other. Okay, so I'll describe this in detail. But again, the flow, I'll take my training instance, the ILP, convert into a graph, convert the graph into a vector, and then project these vectors into another space such that similar problem instances have small distance in between them in that space, basically Euclidean distance. So let's look at each one of these steps. All right, the first one is converting an IMLP into a bipartite graph. This is kind of a standard trick in the literature. we're going to basically create nodes that corresponds to the variables that I have in the problems, x1 and x and in here. And each node will have a label that's basically the coefficient you have in the objective function. Each one of the constraints will be translated into another node, the other side of the bipartite graph, that has a label, and that label is basically the value for the constraint. And now we're going to create edges between every variable and every constraint, and the value for that edge is basically equal to the coefficient that we have in here. So basically A11, you can see between x1 and this first constraint. AMN in here is basically between xn and the last constraint is represented by this node. So by doing this, we can actually represent a mixed integer linear program as a graph. The next thing is we want to transform this graph into a vector that we're going to then use to compare the similarities between the instances. So in here, the trick to convert a graph into a vector is basically using graph convolution network. So we'll take the bipartite graph that corresponds to my mixed integer linear program, run a graph convolutional neural network, and that eventually gives me a vector that summarizes basically kind of the characteristics of this graph. The graph convolutional neural network we're using is 4 layers. It's the standard in the literature with 64 dimensions of hidden layers. The output from the convolution layer is passed into the batch normalization, followed by a max pooling and attention pooling layer. Eventually, the whole graph or the whole ILP instance is summarized by a vector of 256 entries. So that's at the end of the day, each instance gets mapped into 256 elements. Of course, the big question is how can we actually figure the weights in this graph convolution network? So I'll describe that as we do the learning. So if you recall, now we've done with the first two steps, how to encode an MILP as a graph, and then how to encode the graph into a vector using graph convolution network. Like I said, at this point, each graph is a vector, but there is nothing that says graphs that have similar costs or that corresponds to instances that have the similar costs will lead to graph vectors that are close to each other in Euclidean space. And that's where the third step is. That's the metric learning. So we took one of our, there's 1,000 problem instance or 10K, I think, actually instances in one of the problems we have. And we looked at the cost for each one of them. And if you do T-SNE visualization, that's basically the embedding for the 10K instances. And the color of each instance, the dot, represents the best cost that you would get under the same configuration in here. So some instances you see have high cost with this configuration, some instances have low cost and so forth. Now you see that's basically an embedding in here for that vector space that's coming out of the graph convolution network. But you can see in here that if we run this idea that I mentioned, it's not going to work, because you can see if you look at this problem instance, it's not surrounded by other problem instance with the same cost. If you look in here, it's not necessarily surrounded by problem instance with the same cost. What we want to do is project these vectors by multiplying them by a matrix W, such that in the projected space, problem instances that have similar costs are close to each other in that space, in that new space, and by Euclidean space. So you can see in here, this is happening. You can see already all the problems with high costs are basically moved in here to the right, a little bit of intermediate cost, and then finally in this area, these are the problems with low cost. So once we have this graph, if I have a new problem instance, I need to map it into that space, right? Transform it into a vector by the graph convolution network, map it into the space using W, and then basically pick the instance that is closest to it and apply that configuration for it in the solver. So in order to learn this W and the graph convolution network, we're going to basically, again, use this idea of triple sampling. That's why it exists. In here, this is how the learning flow is. This is basically the computational graph for the learning flow. We have 3 problem instances from our training data set. The main problem instance, the anchor. Another problem instance, the positive. That's another instance that has similar cost. Like this one was 100, the other one is 105, depending on a threshold. And then there's a negative problem instance, which has a very unsimilar cost to them, like maybe 10, higher, much bigger than that threshold. Each one will be represented by a graph, the bipartite graph. Then we're going to execute the graph convolution network. That's going to create a vector, the latent vector. And given the cost as well in here, we're going to use this metric learning. So the metric learning is we're trying to find this W such that we multiply W by XA, that's the new projected vector. Then W by XB, that's the new projected vector for the other instance. Oops. And then W by XN gave us WXN. And we want to learn these Ws as well as the values for the convolution parameters in the GCN in order to minimize this. So what is the loss function we're minimizing? V, A, and V, P are actually, these are the ones that have similar costs. So we want to make the projected vectors close to each other in that new space. So we want to minimize that distance, Euclidean distance in that space. The anchor and the negative case are far from each other, and we want them to be far from each other. So in that case, we actually want to basically maximize this value. So that's why you see this negative sign. We want to push those guys as far as possible. So basically, that's what eventually creates that situation in here. These are the initial vectors coming out. And once you do the appropriate training, you find the weight and the convolution filters in here, values for the filters, in order to bring the similar problem instance close to you in that space and the one that is not similar far away from you. All right. So for instance, in here we have 3 test cases, item placement, load balancing, anonymous. These were actually released. There was a competition in NeurIPS 2021, how to use machine learning and combinatorial optimization. And there's 3 test cases were from that competition. We were actually working for the competition, but we couldn't make the deadline, but we still had something to work on after the deadline. In here, if you take the initial problem instance before the training with the graph convolution network in here, you will see them there, and you visualize them with TSNE, you see them all over the place. There's nothing that says 2 problem instances that have similar costs and the final solution will be close to each other. But after you transform them with the metric learning, you can see in here they're very highly clustered. Problem instances that have similar costs are actually lying very close to each other in that space. Same in here, you can see it highly in here, see all this clustering happening. Also, it's very clear in this anonymous case, you can see it very highly clustered in this case. So that shows that we can find ways to encode our problem instance such that similar problem instance are actually close to each other in that space. So as a result, when I get a new problem instance, I just go pick up the nearest neighbor and apply this configuration from the nearest neighbors. Here's a result that actually demonstrates that this hypothesis also works. So what when here, I have a problem instance, a new one. I already have my validation training data set. I get a new problem, it's in my validation data set. I haven't seen it before. I want to figure out what's the best configuration. So I take the configuration from the nearest space and I apply it to myself. And I also compare it, what was the cost of that nearest neighbor? If this whole thing was working, we should see high correlation between these 2 costs, that the configuration from my nearest neighbor, when I apply it to the new instance, is giving me similar costs. So you can see indeed in here that when we do this for these 3 problem classes, you can see that it's highly correlated. So this is good news. It shows that actually indeed when you, those are 2 similar problems in the sense that their costs go up and down together as a function of the configuration applied to them. So as a result, if I get the best configuration from one, I apply it for the other, it will work really well. Our system, which we call MILPTune, we compare it to SMAC. So SMAC again is a sequential search process in here. It doesn't use learning in the way we use it. Doesn't use previous configurations. It's just like figuring out the configuration for each instance as it comes. And MILPTune is basically using the repertoire of learned instances to figure out the best instance going forward. We have 100 test cases in our validation data set for each one of these problems, for this one in here and this one, but fewer for this one. So you can see that we looked at each instance. We compared the solution quality from the configuration that we identify using MILPTune versus the configuration that SMAC identifies. So in here, both of them gave no solutions, and within the 15 minutes, no feasible solution. But within the problem that terminated within the time limit, the 15 minutes, we're able to get 60 problem instance with better solution quality than SMAC. SMAC is able to produce results better for only 32 instances. You can see if we do more nearest neighbors, the key in here is basically, if I go just pick the configuration from the nearest neighbor and run it, if I go pick the 3 configurations from the 3 nearest neighbor, apply them and pick the best result, we can see that we're able to eventually beat, we're always beating SMAC, and of course the result gets improved as we use configuration for more neighbors. And this trend, of course, holds for the 3 test cases in here. Item placement, load balancing, anonymous. Just to give you a little background, item placement is a problem set coming from Google. They basically want to take files on servers and basically place them on different hard disks to improve reliability while minimizing the movement of the files. So there's something, again, they're doing it every day or every week, whatever the schedule is. So you're solving the same problem over and over, but with different instances. Load balancing in here also from Google. It's basically trying to schedule jobs on a fewer number of servers and improve while improving reliability. Anonymous, nobody knows really, but some company gave it and said, we have to be anonymous. We'll give you just the problem. So in here, we'll see how many instances actually we win versus SMAC. If we actually compare the quality of the solution itself, how good is the solution we're getting versus the one that SMAC is doing, we're actually getting 86% improvement in the cost than SMAC. And even better, we're actually not doing any Bayesian searching like SMAC does. We're just learning from the past and applying the new configuration to new instances. All right, so that's the first case study in here. So if you recall, if you're still with me, I hope, I said that there's basically three main buckets we can categorize this machine learning for combinatorial optimization. The first one, you use the machine learning to set up the problem. So we've seen some directions there, and we've seen one particular case study on how to set up the configuration for the ILP solver. So the second big bucket is that you're actually using the machine learning in the loop with the combinatorial optimization. And there's been really a lot of also work in that area, and I'm trying to summarize some of them kind of main highlights in here. One popular example that people have seen is that a lot of the decision-making problems we make have a sequential nature. So for instance, if you're doing branch and bound inside an ILP solver, you always have to pick what is the next variable. And there's usually a lot of heuristics in there on how to pick the next variable to kind of branch on. So that's something that machine learning can help. It can help us basically figure out what is the next branching variable. Given this problem, and given the state of the solution so far, that's an important step in here that we see that is different than the other bucket, is that I need to include not just my problem, but that state that I've reached so far. So given how much I've reached so far, here could be a good next branching variable. Or if you're doing, say, a greedy min vertex cover, what would be a good next vertex to pick, and so forth. Also, another approach in here is that you could be switching between predefined heuristics or policy during branch and bound. So again, in branch and bound, instead of actually using the machine learning to choose which variable to branch on, in many cases there are, like I said, there are heuristics people using right now. And some of these heuristics don't dominate each other. So maybe every time we choose a random variable, we actually ask the machine learning algorithm, which heuristic should I choose to pick the random variable? So in here, I could have at my repertoire 4 or 5 heuristics. They are not dominating each other. And I'm just asking the machine learning, tell me which heuristic to use right now to pick the next branching variable. But the actual pickup is done by the heuristic of the variable. We can fine-tune the parameters of the algorithm. So in that case, those hyperparameters we've been tuning, we kind of tune them once before we run the solver. But in reality, like the solver, of course, is iterative in nature, right? It's making sequential decision process. And maybe during that sequential decision process, we need to actually revisit how we're tuning the parameters of the algorithm. So in that case, there's a chance for additional tuning that happens throughout the execution. Another one is linearization of objective functions. We typically, if you have just used the solver as is, you will just use linearize objective function once. But like I said, this linearization and the coefficients in it are coming probably from a machine learning pipeline to determine what are these good coefficients. But maybe now as you're solving the problem, every time you're basically tweaking the coefficients on your linearized objective function, depending on the assignment so far. Given the assignment so far, I think we can tune the values for these objective function coefficients in there and linearize it. Also, we can identify bounds to the solutions to the problem. This is, of course, very important to kind of bring down the primal duality gap in a rapid way. And these bounds could be also used by machine learning. Given this problem instance, and given so far we've reached, here's good bounds for the problem. And of course, you can combine many of these steps together. In fact, this graph in here that this nice graph that I'm showing from this particular paper, it's actually combining 2 methods. It's basically, it's doing neural branching. It's deciding on which variable to branch in the branch and bound using a neural network. And at the same time, it's doing some pre-assignment for some of the variables before even doing the branch and bound. So basically, it's combination of the first bucket and the second bucket. In the first bucket, where I said, let's resolve some of the decision variables before we solve it. And then even when we're solving the problem, we can still use machine learning to figure out what's the next variable it is. And they show results that the primal dual gap in their cases is much less than existing methods in there. So again, in this type of machine learning and for combinatorial optimization, there's one crucial difference compared to the first bucket is that not just we need to include features about the problem instance, we need to actually add dynamic features as we're solving the problem, we're resolving some issues, and that should impact the state of how we're encoding it. So we need to encode two things, static and dynamic features based on the problem. The last bucket is for the machine learning for combinatorial optimization is basically you're using the machine learning directly to solve the problem. So you're replacing the hard rules in your algorithm. You had hard rules about a greedy algorithm or a combinatorial optimization algorithm. I'll pick this variable, then branch, and I don't know, get the cutting plane. These are hard rules. In here, we're basically the model itself is learning what are the right decisions to make. And there's two big buckets in here, or sub buckets. The first one is surrogate modeling, and you know, one simple way, for instance, you can think about it is that I'm solving different problem instance every day. I can cache the results, and if I see a problem instance that is exactly similar to the one that I've seen before, I will use the cached result. But if I see a problem instance that is slightly different, you know, I can't use my lookup table, but that's where machine learning is good. Machine learning is always good about generalizing patterns in the data. So in that case, we will use machine learning as our kind of approximate lookup table, or a good generalized lookup table. So this is a popular area. They call it surrogate modeling, and there's a lot of work on the surrogate modeling, especially in industrial flows, because a lot of the problems there is in runtime. You have, you have networks routing problems that are millions of nodes you have to run every day. So it would be nice if we can actually, at least for some routes, we can say use a surrogate modeling and basically get the results right away. Another big one that people, of course, have been very familiar with in the last few years is reinforcement learning. And reinforcement learning in here, we have an agent that's learning what are the right decisions to make. It doesn't have any hard rules. It just applies the decision, look at it, applies a particular action, that's a decision. It looks at the state of the system and the reward that it gets from the environment. Am I improving the cost? Is the cost getting better or worse? But of course, it's in the simple version, you have the multi-armed bandit, which basically is just looking at the immediate reward, and that's what it's trying to maximize. But of course, in reinforcement learning, you're trying to maximize the long-term reward. So you're doing more of these actions, and then basically looking at the long-term reward and seeing how things are getting better or worse. You could also potentially use the machine learning to do an optimization in one of these cases, and that would be the starting point for a subsequent algorithm, optimization algorithm. So in that case, it's similar to the first bucket in the sense that you're setting up the problem, but in here you're actually solving the problem to some extent. But then maybe you can tune the results somehow by the combinatorial optimization algorithm. So in that case, these machine learning algorithms, if you do it right, you get great result, but there's not always guaranteed that you'll get an optimal result. So in that case, there is still potential room for improvement if you apply a combinatorial optimization afterwards. I'll describe to you in here one work we've done on circuit optimization. I know many of you are actually in here from a circuit background. I think it's one of the foundations in TILOS. And the tool we were looking in here is logic synthesis tool. And if you're not familiar with logic synthesis tool, the way they work is that the circuit is represented as a graph to begin with. So that's fantastic news that the problem is already encoded as a graph versus something like the ILP. We had to encode the mixed integer linear program as a graph. And these graphs, basically, you can apply transformations to them, and that will change their area, which of course means money, silicon. That's silicon in our case. And timing, which is the delay on how fast it will run. So for instance, let's take the one on the left. These asterisks mean AND gates. Of course, most people familiar AND gates and an OR gate in here. So in this case, I can restructure this kind of subgraph. I can make it x1 ANDed with x2 or x3. So you're basically taking x1 common. So that's one way to restructure. In here, it changes the area. Now I'm using 2 gates instead of 3. The critical path, or the path with the worst delay in this graph, hasn't changed. It still has state. It has to go through 2 nodes in here to go from an input to an output. Here's another transformation, basically, which we call balancing. In balancing in here, I'm ORing 4 variables, and I can OR them in the way in the left, or I can OR them in the way on the right. The main difference is that the critical path, or the path with the largest delay on the right-hand side, is less. So this is a transformation that doesn't change the area. We're still using 3 gates. But it has less delay, and so forth. There's so many commands in this logic synthesis tool, and typically you would apply those in sequence. You apply one command, you get the new result, and this new result or the new graph opens the door for more transformations. You apply more transformations, which open the door for another optimizations, and you keep on doing this, applying the sequence of command until you don't see the result improving anymore. So that's how it looks like. You start with a graph, you apply a transformation and the logic synthesis tool. It gets you a new graph, which you use now as your input, apply a new command, get a new graph, and keep on doing this. And the result you get is highly functional of which commands you're actually choosing. So for instance, this is a result on one small circuit, and I'm evaluating the area and the timing for the circuit as a function of those sequence of commands that we apply to the logic synthesis tool. So in here, we have 6 primitive transformations that, like the 2 ones that I mentioned to you, there are 6 of them, and I wrote them in here for this logic synthesis tool. And like I said, the result depends on the sequence of these commands, which commands are you using and how which one is applied after which. So we have a sequence in here of 24 commands. And each one of the dots in here represents the circuit or the graph that you get after applying one of these sequences. So you can see in here that the result is all over the place. Your area could be anywhere from 1,100 micron up to 1,400 micron, or the delay could be anywhere from 200, maybe 35 picoseconds to 300 picoseconds. There's a large range in here depending on which sequence of command you use. So what is the best sequence we use? Well, if you look at the literature in the past, people use greedy algorithms. Also, there's a lot of it in expert creating those scripts. You always have these, a lot of the cat companies have these kind of recipes that are been passed from generation to the other. This one really works well. Give it a try, right? And how can you find this best sequence of commands? So this is what we want to do with reinforcement learning. So in here, the logic synthesis, the environment in here for the reinforcement learning is the logic synthesis tool. And then this is basically my reinforcement learning environment. We're gonna have an A2C agent, that's my reinforcement learning agent. The agent will take the graph output from the circuit, that's the state of the system, okay? That's the equivalent of the state of the system. And then that agent will pick one of the 6 commands as the optimization that it applies to the tool. It says, okay, given this current state, given this current graph, I'm gonna choose one of these 6, and here it is. And then when it applies this, it's going to get back a reward, right? The area increased, the area decreased, the timing is met, the timing is not met. And it's going to try to learn what is a good sequence of commands to apply in order to maximize the long-term reward, which is the final area you get from your design and whether the design has met the timing constraint that is given to it. Now, the tricky part in here is most of the port components in here are standard. The circuit is already represented as a graph, so we already extract features from it based on graph convolution network and other graph properties like number of edges, number of nodes, and so forth. So we can easily create a feature or a state that encodes the current graph. The optimization is already one of these 6 commands. The reward is a little bit tricky because we're talking in here about 2 objectives we care about. In circuit design, if you're not familiar, there's 2 things you care about: the delay, and that usually is a constraint. I want to meet, say, 100 picoseconds, 1 nanosecond. This is kind of my delay constraint. I want to meet that constraint. And then I would like to optimize or minimize the area as much as possible while I'm meeting that constraint. Because area means silicon. That's money, basically, how much it would cost to fabricate your circuit. So we create a reward function in here that's trying to combine these 2 together. So let's kind of go through some of these entries to understand what's happening. If the circuit meets the delay and the area is decreased, that's basically the best reward we can get. We met the time and we're reducing the area. That's like we applied an action, and that action made us meet the delay and decrease the area. Fantastic, we get the highest reward. If it meets the delay but the area doesn't improve, that's a cost of 0 because it's fine. And if we meet the delay but it makes the area worse, then that's just a little bit of a negative reward. Okay, we would rather prefer to decrease the area while meeting the constraint, rather meeting the constraint while increasing the area. If we don't meet the constraint, then there's still few things are happening. You could be either decrementing the constraint, the delay, but you still haven't met the constraint. You could be not changing the delay at all, or you could be incrementing the delay. So in here, things get a little bit complicated. If you are decrementing the delay and you're decrementing the area, that's still a great reward. Fantastic, I'm heading in the right direction. Hopefully I'll meet the delay soon, so we give it high reward. If I decrement the delay and I don't improve the area, it's still 2 positive, so it's still a good reward. If I decrement the delay and increase the area, I'll still give it a positive reward because the delays are constrained. We want to meet the delay, so it's always have higher priority over the area. And the other thing to remember, if you're not familiar with logic synthesis, sometimes actually you can, to improve the delay, you would have to increase your area. Sometimes it's solely acceptable. You want to reduce the delay, that the transformation increases the area automatically. Let's pick another entry. For instance, if you apply an action and you haven't, you basically increase the delay and you increase the area, then that's the worst reward you can get. We want this to be negative, negative, never. Very negative reward in here. If you increase the area, but you increase the delay, but you optimize your area, you get still a negative reward for that. So the point is that in here, the problem is a little bit tricky because you want to have an objective, you want to have a constraint, you need to combine them in the reward function, and that's the way we do it in here. And then the rest basically falls into the typical framework. We have the logic synthesis environment. We encode it into a graph. It's already a graph, but the standard graph in here is called AIG, which stands for AND inverter graphs. And AND inverter graphs can represent any kind of circuit you like. So we encode a feature that's basically the state vector that goes to our critic actor network. And the critic actor network will give us the transformation probabilities. It's going to give a probability for each one of these actions we have, the 6 commands, and then we pick the one that has the highest probability, and that's the one we apply to the logic synthesis environment. And then, of course, during the training period, you're training this over a whole epoch. You're applying multiple, multiple commands and seeing what happens at the end of the day. And automatically in the learning process, the agent will automatically train the weights in here to identify what are good probabilities. So we had a validation data set for training. Some circuits were used for training to train the agent. And then some other ones were basically used just for validation. And these are the ones that I'm showing in here. I'm showing in here the iterations. As you're doing, the agents apply one command, and then it gets the state of the new system, and then applies a new command, and so forth. We're plotting the area and delay for 3 different circuits in here. So let's see what happens. Let's go through one of them. As you go through the iterations, you see it's actually the dashed line is the constraint. So the constraint in here for the circuit as given to it is 7.5 nanoseconds. So when we started the optimization, the initial circuit was at 9 nanoseconds, was violating the delay. And you can see over time, as the agent works through it, it's basically reducing the delay until it finally hits 7 nanoseconds, and that's less than the constraint we're given. At the same time, it's trying to minimize the area, but like I said, there's nothing that guarantees that actually those 2 things go hand in hand. And in fact, they sometimes, in many cases, go opposite to each other. You're trying to minimize delay, the area goes up, and the trick is to try to minimize the area as much as possible. So as long as the area is not going up too much, that's what you want to do. You want to just minimize the area. In here, you see a situation where we're able to, in all cases, we're minimizing the area, but I'm saying like there is nothing that necessarily you can see the area going down. In here, you see the opposite a little bit. You see the timing is going down to meet the constraint, and the area is also going down, being minimized in the process. So you can think of it in here as the area is as minimum as you need to meet the constraint. In here, the area is minimum as you need to meet the constraint, but it happens to be going down. Same thing in here. I have another circuit. The delay constraint is 4 nanoseconds. You can see the agent is working really hard on the timing. It eventually went over this hump, went down, and eventually it meets the delay at 4 nanoseconds. And meanwhile, the area is being minimized in the process. Compared to the greedy approaches and those expert scripts that I mentioned, drills, which is this logic synthesis framework, it gave us synthesized circuit with 53% less area while able to meet more timing constraints than these previous approaches. We also have it as an open source on that link if you would like to try it. So to conclude, the combinatorial optimization usually have problems in scalability and or quality of results if you impose a time limit. And that's where the opportunity for machine learning to come in. And the key point in here is that we're seeing in most industrial settings, you will see problem instances on a daily level that are basically instances from the same distribution. You're solving the problem over and over and over, but it's not the same problem. It's slightly different coefficients, maybe one or few less variables in it, but everything else looks very similar. And we want to be able to leverage machine learning to basically use previous solutions to aid this the solving for the new instances. We've seen 3 main buckets. One of them is you basically run the machine learning in order to set up some parameters for, say, the optimization problem, or to a priori decide on some variables before you solve the problem, as a result reducing the improving the scalability of the problem. The second one is that you're augmenting the combinatorial optimization in the loop with the machine learning. you're augmenting the optimization in the loop with a machine learning algorithm. So in that case, we're usually talking about sequential decision process making, and every time I'm making a decision, so as a result, the machine learning can help me in making that decision. The third one is substitution the optimization algorithm together. We don't need to have hard rules on how to actually solve this problem. We can instead use agents or surrogate models that basically will learn how to actually solve the problem rather than having hard rules inside of them. I think it's a pretty exciting field with so many potential opportunities, and of course, TILOS is testimony for that. There's many challenges in this area, as you would get in general with machine learning. Having high quality data, I think, is always the biggest challenge. Having good high quality labeled data will be always the most important thing. And not just having high quality labeled data, being able to access the data itself is very important. In some fields, it's easy to access data. In some other fields like CAD, it's very hard to access data. And we can talk a lot about this. A lot of the problems in CAD are actually because the data is locked in proprietary databases. Or no, it's not even a database. They call it database, but it's not a database. It's some company-based format. If things were actually in regular databases that I can run SQL queries on it, then in that case, we open the space much more to have the typical data pipeline and machine learning applied in there. So, and that's one of the biggest challenges, I think, for some of the fields. The other second challenge, of course, is the modeling. Which model to pick? If I'm going to pick one of these machine learning models and I'm going to encode my problem, I can potentially have a number of choices, and that's going to be also a big challenge for you as you're trying to figure out how to solve this problem with machine learning. Generalization in here is also a big factor. So if you notice in here, we had three different problem classes. Each one had 10,000 instances. If I learn the best configuration from one class of instance, can I somehow move it to another class? We were always kind of in the same class of instances, given this instance, which one is close to it from the one coming from the same distribution. So generalization in general is also a big topic in here. Or for circuits, people doing circuits, if you learn something from one circuit, does this mean that this model you learn will generalize for other circuits, or it's good enough for that circuit that you spend the effort for? Scalability, I mean, combinatorial optimization has scalability issues, and so is machine learning. I mean, training the data will be gigabytes or terabytes of data, depending. The machine learning model itself could have, billions of parameters as well. In many cases, you'd have to deploy it on the cloud with many machines running in parallel with GPUs, etc. So scalability is also a challenge for machine learning. And also in this area in here, sometimes feasibility could be a problem. For instance, in the case of the mixed integer linear program, and you're using some surrogate model, who says even that the solution is feasible, that it respects the constraints? So there's one thing, I need to minimize the objective function, but I also need to meet the constraints. And sometimes meeting the constraints with machine learning could be itself hard. And actually, there's a lot of interesting work in that area in the last two, three years. So that's the summary in here. These are some papers that I basically refer to throughout in here. And thank you again for inviting me and for the attention. And thanks to Abdurrahman, who was on the call as well, since he worked with me on this topic. We'll take the questions now.
Thank you. Questions? Well, Sharif, is not only access to data, but access to compute resource an issue that you see in trying to do this from both academia and industry?
Yeah, definitely. I mean, the compute resources is a lot of money. So in Amazon, for instance, we have an AWS fleet, and each team actually pays for AWS fleet it uses for these data pipelines. And typically, we're running each team could be paying like hundreds of thousands of dollars just to kind of use the team for their data pipelines. The one thing I could say definitely the problem with CAD, I've realized it now that I've been in industry for a while, is that the problem is not in the machine learning models. The problem actually is in the data. Access to data is very, very difficult. In most industrial settings, the data is actually sitting in standard databases. With standard tools like SQL, you can run queries of SQL on large data sets spread on hundreds of machines, and you will get the results you want right away. And I don't need to even understand what the tools are doing or the algorithms the tool are doing. I don't need to write C code to parse Liberty formats or def formats or anything like that. All of these files that are sitting in standard databases that I can run an SQL query. I can join them. I can then produce a table that I give as input to pandas and NumPy and run the full machine learning pipeline and get the result. So right now, I think the problem in CAD is basically that things are locked in proprietary databases or in databases that are quote unquote database. They're not like a true data SQL database or NoSQL database. So, and that basically restricts how you can get the data and who can actually get that data. You have to be a programmer, you need to have a source code, you need to be able to parse these things. And you worked a lot in this and with OpenDB and OpenRoad. So it's much different in other fields.
Right, and IBM folks such as Leon Stock or others had always been pointing us to kind of use commodity infrastructure,
Yep.
Neo4j and so on. And it's very hard to get, as your students experienced in OpenRoad, very hard to get dyed-in-the-wool CAD and chip design folks to make that leap, I guess.
Mm-hmm. Yeah, I mean, you already have like decades of baked infrastructure already in these formats and all of these things, and it's tough to kind of break loose off them.
Are there other questions? Raise your hand or jump in. Otherwise, Farnaz.
Somebody, Ismail. I see a hand raised. Ismail.
Oh.
Ismail.
And Farnaz also. So
Okay.
Ismail and then Farnaz.
Hello. Great presentation and nice talk. I really enjoyed. I have two questions regarding the first approach you mentioned. In the first approach, you introduced the similarity or distance metric for the integer programming problem. When it comes to other problem types, what would be and how easy would it be to define such similarity metric?
Good question. I mean, in here, I guess, the same framework could be used, no problem. The question is really, what is the metric that you will use, right? That you want to say, I want to bring this two instances together based on a certain metric. And in here, it was the cost for the different instances under the same configuration. So I guess it has to be, like, I can say something, but we have to look at each problem instance and try to find something like that, right? If you're trying to configure an algorithm, what would be those parameters of the algorithms that would lead to maybe similar cost in your case, whatever your objective function you're looking for, or maybe whether they would meet this constraint or not meet the constraint, things like that. So I think it would be highly dependent on the problem, and we have to, look at that. And I mentioned one of the challenges is the modeling always, right? So I think that's the part where some of the effort will have to be spent there to understand what's the best way to do it.
Thank you. And the second part of my question is somehow related. Did you get into a scenario where the parameters defining the problem behave in a chaotic manner, meaning a small change in the problem parameter produces huge changes in the nature of the problem to be solved, and this creating problem in defining the similarity metric?
Abdurrahman, maybe you want to, since you worked with the data firsthand, maybe you want to say if you actually encountered something like this while you were training.
So can you repeat the last question again?
So the question is, did you encounter any scenario in the integer programming problem or any problem type, perhaps, if you try to define the similarity metric to face a scenario where the problem parameters are behaving in a chaotic manner, meaning that a small change in one of the parameters of the problem that you are solving, it can be one of the constraints or just changing a small node, creates a huge difference in the nature of the problem, and that becomes a bottleneck, a problem in defining a similarity metric, because the situation is not smooth.
Okay, got you. So as far as this work has focused on, one main assumption that we have built upon is that all of these problems are coming from the same distribution. And when we say the same distribution, that's a very specific word that we refer to, that all of these problems represent the exact same problem definition. For example, it's item placement, or is it load balancing, or is it a problem that is solving vehicle routing, and so on. So the fact that the data set that we have worked with is problem specific, it's coming from the same distribution, is making things a little bit easy here. We haven't encountered an issue where a small change in the coefficients of the problem or a small change in the coefficients of the constraints itself like make a dramatic change, because at the end of the day, when you look at the range of the costs that you get, for example, for one problem, it's between 0 and a specific range, and then there is no solution. There is a maximum for the cost. And assuming that you are giving the same hardware resources, the same time limit, and the same solver version, because this is very important. When you use different solver versions or different hardware resources, actually it makes this one makes a big difference. But assuming that all of the other constraints, like the same tool, same version, same hardware, same time limit, and you are using the same constraint configuration, then this is the definition of the similarity. Another thing I might add in here is when we look at the literature for similarity learning, similarity is very subjective word, meaning that I can give you 2 pictures of a car and ask you, are they similar? And you say, yes, they are similar because they are 2 cars. But then I can give you 2 pictures of cars, one is blue, one is red, and I ask you, are they similar? You say, no, they are not similar. So this is subjective. How do you look at these 2 images? Is it because they are 2 different objects, or because they are 2 different colors, or maybe they are 2 different models? So for some problem domains, as long as they are 2 cars, that's fine. They are similar. But for some other domains, as long as they are like 2 different models of the car, then they are dissimilar. So the choice of the objective for the similarity is very critical as well here.
Yeah, fair enough.
Does this answer your question?
Yes, thank you. Appreciate it.
Okay.
Farnaz, go ahead.
Farnaz?
I mean, if you don't have time, I can just connect.
No, go ahead. Yeah, no, go ahead, please. Go ahead.
And Yusu had a question before she had
well,
to go.
Why doesn't Yusu just go ahead and
she wants me to ask because she had to go run a meeting. So I have it.
Why don't you
chat.
ask? I actually wanted to reconnect with Sharif, so I'll do that.
Oh, I see.
Yeah.
Okay.
Go
and
ahead.
I have one on. Does anyone?
I have to run actually after this right away. I have a meeting with my manager at Amazon. I can't keep him waiting a long time.
I heard Amazon's a really gentle company, Sharif, so don't worry. Here's her question in chat. On the theoretical front, what has been learned? What kind of generalization, performance, or extrapolation to unseen data of different sizes you've observed?
So I think this is actually almost looks very similar to the answer that Abdurrahman was saying, that we have been working on the same distribution of problem instance. So things have been working on that space. We haven't to try to do cross this, do generalization cross the problem the problem instance. So it's very similar, I think, to the other question.
Okay, fair enough. If you have 30 seconds, does anyone pester you about explainability? Because,
oh yeah, of course.
Okay, and what do you say? What do you say to them?
Because I actually say that it's better to use simpler models. It's better to use simpler models that you can explain than another complicated model that improves things by 1% that I cannot understand or explain. So that's what I tell people actually in here. And actually in Amazon and other places, it's very important, because when we're solving this problem, we're solving it for business guys. So business guys that want to understand, why is this happening? Why are we choosing this solution? So it's not technical guys. These are actually business guys. We're solving business problems with these tools. So in that case, explanation becomes even more important. And as a result, simpler models that could be well explained could be better than more complicated models that are not explainable, but give you just a little bit of an improvement.
Okay. Well, please reconnect with.